First, let's look at the computer that's going to run Lamini. So let's go to the data center, look inside, and we can see the MI300 server that we're going to run this on. These are powerful computers. This is why they call it a large language model. Okay, let's log into the machine. Okay, we logged in. So let's look at the GPUs. So we have 8 MI300 GPUs. When we're bringing up the node, we use this Ansible playbook to install all the dependencies that we need. It installs Kubernetes, and we use high-performance networking, which is provided by Rocky, which is RDMA over Converged Ethernet. And we also include the GPU drivers and, in this case, the AMD GPU stack. On NVIDIA, we would use the NVIDIA GPU stack. So let's look at how to install Lamini. We can get our release. This one is v1.4. We typically do weekly releases. And we can get the installer that we want. So let's say this is an AMD cluster, so I'm going to install using Helm for AMD. So I'm going to grab that. Next, I'm going to open up the cluster config file. So this is going to let me determine how many GPUs I'm going to assign to different services. So in this case, I'm going to start up some inference servers and some training servers. Now from here, we have an automatic Helm chart generator where we just basically run a script and we get the Helm charts that we need to be able to install this cluster. You can look at the chart. It's going to have the services that we can then Helm install, and we can get our pods up and running. 8 inference workers that are running on 8 different GPUs that can be used to run inference. We have a training controller that allows us to do tuning and memory tuning. And we have 3 worker nodes that add up to 24 GPUs that can be used for training, tuning, memory tuning. Pods to ever connect to the internet or to connect outside of the system. So that means that when you use this system, your data is secure. It can't leave this system. We're actually running the Slurm scheduling system with an MPI environment and a high-performance networking environment inside of Kubernetes. So let's look to see what's happening inside of the cluster. Well, it looks like we're running over 10 jobs. Some of them are actively scheduled, and some of them are waiting in the queue because they don't have enough resources or they're not at the front of the queue yet. And we can see some of them are using multiple nodes and multiple GPUs per node. And some of them are using multiple GPUs on a single node, and some of them are just using a single GPU. So now that the cluster is up, let's log into it. What year did David Aguilar climb the Golden Gate Bridge? And the model doesn't really know about it. How do we remove these hallucinations? How can we teach it new information? Let's look at that next. This seems like a pretty straightforward fact. Let's see if we can find the ground truth. How do we even know what the right answer is? Let's go find a reference. We can look it up. Let's try Wikipedia. Great, so you got the Wikipedia article about the Golden Gate Bridge. And let's see if it says anything about David. Oh yeah, there he is. May 1981, Dave Aguilar climbed the south tower of the Golden Gate Bridge to protest offshore oil drilling. That's interesting. So one of the things that I personally find surprising is that this is a public reference. This is Wikipedia. LLMs were trained on data that was scraped from the internet, which certainly should have included Wikipedia. I'm 100% positive that the LLM has seen this training example before. So even though it was included in the training data, why did it hallucinate? Why didn't it get the right answer? Next thing I did is I want to get an idea of how well the model does on questions that are pulled out of this data set. Most of the process of training an LLM can be automated, but this part where we construct an eval, it's very important to do it manually. And the reason why is because you as a human want to make sure that the answers are exactly right and that you know the types of data that you have and the types of mistakes that the LLM can make. So we typically create a what we call a golden test set. This is the golden test set for the Golden Gate Bridge. So let's look at our little eval script. We're going to use the Lamini library. We're going to import Lamini. We're going to import these concepts of a generator, a prompt, generation pipeline, and a node in the generation pipeline. And this is going to be a pretty straightforward pipeline, but one of the strengths of Lamini is that we can process all of your data very quickly and efficiently over a big cluster. So this pipeline lets us distribute the work from running all of these requests over the whole cluster. So let's run it. So running it. Now you saw I already created a cluster. So this, you can see the gory debug mode, is going to connect to that cluster and just submit all these requests. One of the things that you can see here is that we're actually connecting to the cluster, realizing that there's enough GPUs available to submit, in this case, 20 requests at once. And we're going to submit 20 at once. They're going to start coming back. We use this kind of batching pipeline so that you don't get rate limited. Effectively, you can have a lot of users who are all competing for the same cluster, in which case there are probably other users of this cluster, but I'm still able to submit pretty big batches, and my application isn't getting rate limited. None of these requests are failing. Switch over to the spreadsheet where I've already loaded this up. So let's look at some of the questions and answers. So here's the first one. What year was the Roundhouse Cafe Diner completed? Correct answer, 1938. The model Llama 3 doesn't really know about it. I'm not aware of that. Let's look at some other ones. What year was the Golden Gate Bridge and Highway District Act passed by the state legislature? 1923, but the model confidently says it's 1928. So in the same vicinity, but not exactly right. Probably the model hasn't seen this fact before, or it didn't train on it enough when it was originally being trained. Some of these, that are just very straightforward facts, like what is the color of the bridge? Orange. It's pretty obvious. What is the length of the Golden Gate Bridge? 42,000 feet. That's a, main metric of the Golden Gate Bridge. So the model is doing pretty well for these really obvious things, but what about something that's, not quite so obvious? Let's look at this one. What was the cost of the movable median barrier system, including the zipper trucks? My kids love driving over this bridge and looking at these zipper trucks. Let me actually see if I can find an example. Zipper truck, Golden Gate. This thing, it is a really cool looking truck that just drives over the bridge and moves this barrier. My kids love this thing. I don't know why. It looks like a caterpillar or something. But in any case, it evidently cost from the article $30.3 million to build this thing. The model confidently says it's $40 million. If I was actually using the model to set up the contract for this thing, I would not want to pay an extra $10 million if I was paying for this. So you can kind of see how this can be problematic. And if we go over the whole test set, this has about 30 questions. This gets about 10. The base model gets about 10 out of 30, right? So that's about 30%. This is a common document, right? This is like a Wikipedia article. There's all sorts of stuff on Wikipedia, and the model was certainly trained on this. So even though it's a really common application and like really common set of questions, and this data was absolutely trained on by this LLM, it still hallucinates 60% of the time. If I was doing a threat assessment, I would not want my name to get hallucinated. So next, let's use memory tuning to remove some of those hallucinations. So if you remember, we had this text that we got about the Golden Gate Bridge that has all sorts of facts about it. So how do we turn this into training data? So here we're going to exploit the idea that the LLM can read. Maybe it's tough to recall all this information from memory, but if the LLM is reading like a paragraph at a time, it can clearly read, and it should be able to pull out the facts accurately and precisely. So let's build another pipeline to do that. And this is the prompt that we're getting at. So, you're an expert in the Golden Gate Bridge. Please read this article carefully. Here's the information. Let's just go through and run that. There we go. So now we can kind of see what we're looking for. What year was the program to improve corrosion protection completed? 1995. How many painters are responsible for maintaining the paintwork? 38. Okay, so now we're getting somewhere. So now we have a pretty diverse set of different questions and then factual responses. Let's learn how to teach this data to the model. Just going to make a new new directory called train. Go in there, make a little training script, and we can look at our training script. So we're going to load the data that we just generated, and we're going to call LLM tune. This is going to use memory tuning. Looks like the queue is actually fairly deep. The queue has a lot of things in it. One of the really difficult problems if you're running a cluster that has a lot of training going on in it is fault tolerance. These jobs can fail for all sorts of different reasons, like what if someone pulls out a cable, or the node restarts, or the network drops a packet, or the node crashes, or the GPU overheats, or the disk runs out of space, or there's a memory error. There's so many. So you put all that stuff together, a lot of machines all working together for a long time. What if something goes wrong? This big job is taking up a lot of space. Let's kill it. So is this one. Let's kill them. And let's see what happens. So we saw, well, okay, they got cleared out, and the nodes are now free, and our jobs have started. Oh, look, they're all started. Still is in progress again. We basically have checkpointing. You can also see we're adding our mixture of memory experts adapters. Right here, it was training happily, and then killed signal 11. But look, it's back. And it's resuming from where it saved its progress, and it's going to keep going. It's loading itself from a checkpoint. It's going to keep going. So we've put a lot of effort into verifying hundreds of failure cases and have a very extensive test suite that goes through and checks all of these different failure conditions so that no matter what happens, your important long-running jobs, expensive jobs can keep going. And this is the one that we just launched. And as we can see, it's starting to train, and the loss is going down. Let's take a look at our model when it's trained. Memory tuning is not like normal tuning. Normally, we're not trying to get the loss to be this low, but for memory tuning, in order to get the facts exactly right, the loss actually has to go down pretty low on these. I'm going to run the eval. This is also noting a pretty important feature of Lamini that, well, I have 11,000 models, and I just called inference on one of them, and it just finished pretty quickly. So how did that work? Well, in the back end, we have all of our experts that are stored, and we load them quickly, dynamically. We've heavily compressed them, so that we can move them around really efficiently to all of these inference pods. And there's no separate deployment process. As soon as the model is trained, even as it's just begun training, you can immediately start using it, just like I did. So let's go look at the results. It turns out I've already loaded in the results, so let's see what they look like. Okay. What year was the Roundhouse Cafe completed? 1938. Well, now the model gets it right. Exactly. And look at that across all of these different things. Let's, we also want to make sure that this is still a reasonably good model. Like, what if I ask it something like a little bit different? Okay, so let's grab the template and let's try it out. So let's do the zipper trucks. What was the cost of the, what is it called? The barrier and the little zipper trucks on the blood gate. Okay, my kid always loves to call them the little zipper trucks. And let's see, 30.03 million, was that right? Yeah, 30.03 million. So even though we're asking about it in a different way, the same information is remembered by the model. Is trained on this Golden Gate Bridge information. Is it still good at answering questions about other things? Like, can it talk about other things? So I could also ask it, what some different types of cats? Here are some of the main categories. Long hairs,